Welcome back. We're going to start a chapter on acids and bases. We're going to look at the first theories for acids and bases. In your textbook, this is page 206 to 217. By the end of this lecture, you will be able to assign names to acids and base compounds. You'll be able to identify the physical properties of acids and bases. You'll be able to describe the tests used to determine if a solution is acidic or basic. And you're also going to expand your knowledge of acids and bases to include the modified Arrhenius theory of acids and bases. So the purpose of this chart here is just to show you some common acids and bases that we encounter in our daily lives. So partly just to underline the importance of understanding what an acid and base is. Notice that acids are common in food items and also as cleaners. And bases are definitely cleaners as well. Some foods, but mostly cleaners, and then some examples are on the side there. In terms of testing acids and bases, they behave differently to several tests. For example, for litmus paper, acids turn blue litmus paper red, while bases turn red litmus paper blue. pH, they differ as well. Acids have a pH less than 7. While bases have a pH greater than 7. Both are electrolytes, both conduct electricity. Acids have a specialized reaction or a special reaction. If you place active metals such as the group 1 or group 2 metals into an acid compound, they react with the acid to produce hydrogen gas, whereas bases do not. In terms of taste, acids are sour. If you think of lemons, limes, they're acidic fruit and they're sour. Grapefruits. Whereas bases taste bitter, and in terms of feel, acids don't really have a characteristic feel, whereas bases feel slippery. If you take a base solution and rub it between your fingers, there'll be a slippery sensation. So, since acids and bases conduct electricity, that means they must form ions. If you look at our definition of solutions that conduct electricity, solutions that conduct electricity must have ions in them. So both acids and bases have to dissociate in water. And here's the dissociation reactions for acids and for bases. So the first one, this is nitric acid, but it shows a typical dissociation where acids produce this hydrogen ion in water. So when you put an acid in water, you get the hydrogen ion. For this potassium hydroxide, the typical base reaction for dissociation is the production of a hydroxide ion. So that's in terms of how they react differently in water, the ions they produce. And so this was used to form the first definition for acids and bases, the Arrhenius definition of an acid and bases based upon the presence of certain ions in aqueous solution. For acids increase the concentration of hydronium ions. So acids produce hydronium, whereas bases dissociate to produce hydroxide. So just by using that general idea, we can go through a bunch of compounds and see whether or not they're acidic or basic just by looking at how they dissociate. So based on our knowledge of dissociation, the first compound here, sorry, I got to get my pen to the right spot. This would be a base because it's going to produce hydroxide ions in solution when it dissociates. The second one here, H2SO4, would be an acid. The next one would be a base because it's going to produce hydroxides. This potassium sulfate is actually a neutral solution. No hydroxides, no hydrogens, so it's neither an acid nor a base. This one right here, you might be tempted to say a base, but actually when it ionizes, only this end hydrogen comes off. So this is actually an acid. And you'll notice anything that has a COOH at the end, grouped together like this, these are carboxylic acids or organic acids, and as the name implies, they form acids in solution, so only that end hydrogen comes off. So when this dissociates in water, you'd actually get HCOO negative and a H plus. The next compound is a neutral compound. Potassium hydroxide is a base. because the hydroxide is going to come off, and this here would be an acid, as these hydrogens would come off the compound when they dissolve in water. So just by looking at compounds, we can tell often if they're acids or bases based on how they dissociate. Now it turns out that there are some acids and bases that can't be explained by this definition. These are acids that don't actually contain any hydrogen ions in them, or bases that don't contain any hydroxides. And some common examples are the three listed here. Carbon dioxide, we know empirically, is an acid. If you dissolve carbon dioxide in water, that solution has a pH less than 7. This is the acid of soft drinks. So this is in soda. We know it's an acid, but we can't explain it with the definition that we have. Ammonia is a base. We use it as a cleaner. It reacts. It turns litmus paper, or red litmus paper, blue. So we know it's a base, but we don't have an explanation for it. Same thing with barium oxide. Empirically, we know it's a base. It has basic properties. We just can't explain the basic properties with any theory. So we have to change our theory or adapt our theory. So for the modified theory of bases, we say bases dissociate and increase the concentration of hydroxide. So if we're going to stick with that idea, if we still need to form hydroxide ions, we have to explain why something like ammonia is a base. And so while it cannot dissociate to form hydroxide, it can react with water molecules to form hydroxide ions. And we can do this because ammonia is a very, very polar molecule. If we take a look at, so how does it do it here? We'll take a look. Now if we were to draw an ammonia molecule using a Lewis structure, we would see something that looks like this here. And this nitrogen is very electronegative, and those hydrogens are very weak when it comes to holding on to their electrons. So each one of these bonds are very polar. Each of the hydrogens are a little bit positive. And this nitrogen is negative. Now, if we put this in water, if we surround it by millions and millions of water molecules, what can happen is, again, we have another very polar molecule. If we remember, this oxygen has 2 lone pairs on it, and the oxygen end is very, very negative, and the hydrogen ends are positive. So as this water molecule comes close to our ammonia molecule, it turns out that this hydrogen could actually be pulled off and attached to our ammonia. So what can happen after the reaction, or if a reaction is going to happen, is we can actually get an ammonium ion and a hydroxide ion. So one hydrogen's going to come off of that water, and this molecule here is going to be positively charged. Our water molecule now is going to be negatively charged, as it's lost its hydrogen. It's not going to lose any of the electrons that it had, because the hydrogen is too weak to take anything with it. But we're going to end up with a negatively charged hydroxide ion and a positively charged ammonium ion. And so this happens because both those molecules are very polar. Those hydrogens are they're almost lonely little protons floating through space. They've lost that one electron that they hold is being stripped away from them. So it's easy for a hydrogen to get pulled off. And so that's how we're going to modify our theory. We're going to say that bases that can't make their own hydroxides can react with water molecules to form hydroxide ions. And so notice that because they can't make their own hydroxide, and because they're forming ions, we use this double-headed arrow. In your book, you'll see it drawn like this. So it's a two-headed arrow, and what this means is it's an equilibrium reaction, or it's a reaction that doesn't go all the way to one side. And we'll talk a little bit more about that in the next lecture, but for now, that should do for us. So instead of dissociating, they're going to react with water to form hydroxide ions. And so if we're going to say that water can react with very polar molecules, we can also say that they'll react with ions as well. And so here's how we can start. Here's where the theory changes a little bit more. Because that ammonia was a polar molecule, if a polar molecule can strip hydrogens off of water, then ions should also be able to attach themselves to water. And so this is where our definition has to change a little bit. And what we're going to say is, instead of, if we have only little hydrogens, and we're saying this is what acids produce in water. So if an acid produces a hydrogen ion, well, it's surrounded by water molecules when it's in solution. And these water molecules are very polar, and the oxygen has several lone pairs, so there's no reason why this hydrogen can't hop on and form what's called a hydronium ion. And what you end up with is something that looks like this with a positive charge. And so these hydrated protons, or protons that react with water, H3O plus, are called hydronium ions. And so why does a hydrogen bond with the water? It's because water is polar and the hydrogen is attracted to that water. And I'm just going to erase that stuff so you can see the reaction written nice and neat there. But anyways, there we have it. So water is polar, the hydrogen ion is attracted to the negative end of the molecule, and that's what gives us our hydronium ion. So water is now going to be treated as a reactant. Before this point, when we dissolved acids or bases in water, we put the water over top of the arrow. We put it over, made it a dissociation reaction. So one major thing that's changed is now actually water becomes a reactant in our reactions. So the hydrated proton is called a hydronium ion, and the hydronium ion exists because those H plus particles in the solution are continually colliding and reacting with water molecules. And so here's how our definition changes. We used to say that something like nitric acid, when you put it in water, it dissociates. Now what we're going to say is, when you put nitric acid in water, it's going to form those hydrogen ions and those nitrate ions, but because water is polar, these hydrogen ions are going to hop onto water. So what we're really going to say is this. Here's our new reaction. When an acid dissolves in water, it forms its anion, so there's the anion, and a hydronium ion, and it reacts with a water molecule. And so here's just an example of how that might happen in terms of pictures. The top picture here shows hydrochloric acid and water molecule. When they collide, and when they collide the right way, the hydrogen on that hydrogen chloride is going to pop off, and you're going to be left with chloride ions and hydronium ions. So, and this is the currently accepted form of which H plus exists in a solution. So, and notice that it can be involved in hydrogen bonding with other water molecules. And now we're going to turn our attention back to bases, and we're going to say, we'll have both. So here we're going to say an Arrhenius acid, an Arrhenius acid reacts with water to produce hydronium ions in solution, and an Arrhenius base dissociates with water to produce hydroxide ions in solution. So here's our modified hydronium ion theory. So here the big difference is water is now a reactant, and it's a reactant that forms hydronium ions. This is for an acid. For bases, we can say either. We can say either dissociation. For the ones that can dissociate, we're going to leave it as dissociation. So if something has a hydroxide in it, it makes sense to keep our definition as a simple dissociation reaction. If something's a base, but it doesn't have hydroxide, then we're going to react it with water to make hydroxide. And all this is theory to match the empirical evidence. Empirically, we know these things are acids and bases, so theoretically, we have to have something that matches the empirical description. So there are some troublesome acids. For something like carbon dioxide, we know the pH is less than 7, and generally speaking, all non-metal oxides, so things that match up with oxygen and are non-metal, so for example the carbon dioxide, sulfur trioxide, the nitrogen nitrite or nitrogen dioxide. All of these things form acidic solutions. So here's how we explain it. We are going to explain it in 2 steps. The first step is they can't by themselves donate a hydrogen. So we know there's no hydrogen in our carbon dioxide to give to the water. So we can't make hydronium directly, but what we're going to do is the first step for all of these is basically put all of your atoms together. Into one compound. So as we put them all into one compound, so for carbon dioxide, when it runs into a water molecule, it makes this carbonic acid molecule. And now what we're going to do is we're going to take that carbonic acid and we're going to react it with a second water molecule. So here's what we're going to imagine. The carbon dioxide bumps into one water, forms a compound, and that compound bumps into another water molecule. When it does that, it donates one of its hydrogens. So this carbonic acid is going to donate a hydrogen to our water molecule, and that's how we get our hydronium ions. And here's our negative anion as well. So when it transfers that hydrogen, it takes a positive charge with it. And what we're trying to do is make hydronium ions. We know it's an acid, so we need a way to explain why it's an acid. So we do it in 2 steps. One, to make that bigger molecule, and then we take that bigger molecule and react it with one more water. So in the end, we end up with a reaction of one carbon dioxide bumping into 2 waters, or reacting with 2 waters to form hydronium and an anion. We can do the same thing for bases, and again, it's these oxides that give us the problem. Something like calcium oxide is actually basic in solution, and for most metal oxides, this is true. So anything that takes a metal and pairs it up with oxygen, these generally turn out to be bases. So again, we're going to do it in 2 steps. Step number 1 is exactly the same idea. Take all your atoms and throw them together. So all atoms from one water and one of our, in this case we need 2 to balance it properly, but all atoms into one compound. So again, our problem is we can't actually dissociate this to form, we can't dissociate it to form hydroxides, and it can't take actually just one hydrogen, so it's going to take 2. And so we end up with calcium hydroxide. And now that we have a calcium hydroxide, now we can dissociate it. So it's a little bit trickier than the acid one, but basically we shove that water molecule into our calcium oxide, and then we dissociate it into calciums and hydroxide. So here's our overall reaction for the metal oxide bases, and these are really the only 2 special cases we have. We have those non-metal oxides that form acids, and the metal oxides that form bases. And so now we're going to use our modified theory and just do the same thing. And when we go through it, we can see for the most part, not much has changed. If we take a look, hydrochloric acid is still an acid. It's just going to react with water to form hydronium and chloride ions. Same thing here. As soon as you see an H with some kind of anion, you know it's going to be an acid. Same thing with these hydroxides with the metals. So this is going to be a base. I'm going to skip this one at the bottom here for a second. Here we have COOH, so we know this is going to be an acid. It's going to be the hydrogen on the ends that come off and react with water. I'm going to skip that one too. Here we have another base, and so really all we're left with are these special oxides. And so since this is a non-metal oxide, it's going to be an acid, and the other 2 are metal oxides. So metal oxides end up being basic, non-metal oxides end up being acidic, and you should have an idea as to the general mechanism as to how that works.